The last question. So we do slow it down with the force equal to 10 to the 4th newtons in this direction. Delta x equals question mark. Okay, you could solve this with kinematics. The easiest way, in my opinion, is to recognize the kinetic energy before you slow down was what, 1.5 times 10 to the 5th joules, right? And that turns into work done on the road, which is going to be the force, your retarding force, the force of the brakes, times delta x. We can solve for delta x. That's equal to the kinetic energy divided by the force is 1.5 times 10 to the 5th joules divided by 10 to the 4th newtons. Okay, and a joule is a newton meter, so these cancel, and I wind up with 15 meters. We can check this with acceleration. With 10 to the 4th newtons and 3,000 kilograms, my acceleration would be about 3 meters per second squared. If I started with 10 meters per second, and every second I slowed 3 meters per second, it would take me about 3 seconds to slow down. And so 3 seconds times my average speed, which started at 10, finished at 0, that's 5 meters per second. So my average speed is 5 meters per second times 3 seconds. 15 meters. I like it. Okay, so there's a sign. I mean, these are vectors, we remember. Okay? And the force on the car is in this direction, but the displacement is in the other direction. So this should be a negative. But that would be the energy that we're taking away from the car. And so we could say the change in kinetic energy is the work, which is a negative, which winds up being a negative because the force slowing down the car is in that direction, but the displacement is in this direction. At the same time, you could do what Richard Feynman said, and that is if your answer is negative and you know that it should be positive, you change the negative to a positive and figure you're okay. I mean, we know this is the formula for work done. We know that there's a change in kinetic energy, and this is the amount of kinetic energy we have to turn into work.